Welcome everyone to the headquarters of Just Eat in London. Um, so this is Spicing Up Search, the recipe for relevant results, and Mike is going to start.
Cool. So yeah, this is going to be a simple presentation, a bit about our adventure from taking our search at Just Eat from simple text search into the semantic into the semantic realm. And it's going to run through a bit of our journey and also focus on some key spicy findings that we found. So the structure of the presentation is basically that we're just going to go through the problem with our current text search. Then we're going to go through the solution, which is our current fine-tuned model. Then we're going to go through the challenges that we encountered bringing this to life, and also some of the improvements that we brought about to fix them. So let's start with the problem, which is the issues with our current text search model. So we looked at what customers have been saying on the app, both through customer interviews and also through analytics of what people are searching for and whether they're finding results for them. And all of the people have kind of the same problems. My favorite restaurant is closed. Now what? So yeah, a restaurant is closed. It doesn't show up in search results, but nothing relevant shows up in search results. So people feel stranded. They might drop off the app. It's all stuff that we don't want. Similarly, people might want a restaurant that's not on Just Eat. We still want to show results in those cases, even though we don't have those restaurants, and keep those customers with us and also keep them happy. And people who might say that the restaurant was not there before, which usually is because they've made some bad typo and results are not coming up. So these are things that normal traditional text search would struggle with. In the case where people are searching for items, there's also some problems. People might search for brands instead of the item name itself. They might also search for synonyms like nappies versus diapers, but stuff might not be there. And then there's also more descriptive queries like I just want something healthy and high protein, which might not return results with traditional text search. More specifically, the problems that arise is a synonym problem, so diapers versus nappies, soda versus Coke, stuff like that. Abstract topics like high protein and crunchy, which normal text search cannot deal with. And also, very importantly, missing context. So hot and spicy in the context of a food delivery app kind of means the same thing, but yeah, normal text search might not capture that. On top of all that, there's also the problem of uninformative product naming on our app. People get very creative with their names. So the Big Blue is a burger, but in my opinion, could also refer to the sky or the sea. And also even Big Mac, that we all know what it means, normal text search would not be able to deal with. And then there's people who go very sentimental with our search and would go and post entire essays of what they want. But yeah, text search would not be able to do that just because the frequency of relevant terms is not there. So here is where our solution comes in with our fine-tuned model. And I'm going to go straight into how that looks. It's basically a two-tower model based on sentence transformers. It's trained on item interaction data with people using our search bar. So on one side, we put in the user query that went into the model. And on the other side, we will have the item or the restaurant name. And what we're basically doing is embedding both of these. And we have a loss function to basically encourage those embeddings to be as similar as possible based on the search interactions. So this is the basic model, and you're very familiar with it, I guess. So I will now go into how we make it more spicy through our issues. So yeah, we trained, we analyzed, then we adapted. And very early on, we had our first kind of issue. And this is where it starts to get interesting. A lot of the search terms are not very frequently searched for. So I don't want to brag, but Just Eat has a lot of products. And we're constantly growing as well. We're getting more and more grocery partners, and their items just keep on getting weirder. And of course, they have big catalogs as well. But some items are searched very frequently, like eggs, where other stuff like liquid smoke, we very rarely have searches for. So how do we deal with that problem? For some stuff, we rarely have searches for. So what are we basically doing to fix this? here is where two key things come in place. Some other stuff come in place too, but these are our two key main ones. One of them is pre-training on auxiliary tasks, and the second one is pre-training on existing metadata that we have. So I'll explain pre-training on auxiliary tasks with an example that has proven very useful for us, which is grocery substitution. For anyone who doesn't use food delivery apps, grocery substitution is basically you order an item on the food delivery app. Someone goes to pick up the items for you inside the supermarket. They don't find that specific item, and they'll just give you a similar item that they think, that they think is quite similar to that item, in order not to leave you empty-handed in terms of that order. So we found that this is a very nice pre-training task for us, and we could reuse these item substitutions as a first indication of what items are similar, because items that are similar are probably going to be swapped by each other. This is very useful for two reasons. One of them is we're very lucky, and it's related to grocery as an auxiliary task, which is one of the tasks that we really struggled with. And at the same time, it also helps us mine negative samples as well, very strong negative samples, because items might have been swapped by the person that picks the groceries, but a user might not like the swapped item. So we have a very strong negative signal there for what items might appear similar but are not. Oh, I was too fast. Pre-training on existing metadata is then a separate technique that we use. And it's basically on every product, we have a lot of metadata associated with it. One such thing could be category, for example. So we can use that as a kind of pseudo query in our two-tower model to start giving our model an intuition before we even start training on the interaction data on, basically how data might look like in a food delivery app context. And an example for liquid smoke could be, for example, that we might use the fact that it's a condiment as a query. We already know that, so it's already giving us some sort of information. So both of the above methods enable our model to better generalize to underrepresented items, and we've seen great benefits from them, but more issues pop up. Latency is another one that I guess everyone here cares about. I'll go briefly through how our model is deployed, but I'll not go into details. Basically, we have a batch side to everything. So basically, in our data warehouse, we will have all of the information about all of our restaurant menus, grocery partner menus, and we'll basically batch embed those every certain amount of time, and then take those embeddings and put them inside our vector database. And then the second path that you see there at the bottom is the real-time part. Whenever a user searches on the app, we'll basically create an embedding on our real-time endpoint and use that to query our vector database to get our result. The part where most of the optimizations matter is the real-time branch on the bottom. And a lot of optimizations have improved us. For the vector database, of course, the architecture of it plays a very big role. And also for a real-time endpoint, of course, what type of instance we're going to use, how we're going to auto-scale it, whether we're going to use GPUs. A lot of that has brought big improvements. But the stuff I'm going to focus on is more on the model side, and it's two simple improvements. One of them, I guess you all do it, but embedding quantization. So quantizing our embeddings, compressing them to binary or byte vectors. We found that through experimentation to uphold very, very high accuracy for us, while also very much reducing memory and latency. The second improvement is adjusting the number of tokens. So our users might sometimes input very, very, very large queries, other times very small ones. But where do you strike the balance of serving as many users as you can, while also keeping everything speedy? So it was a lot of analysis on the Pareto front on how many queries are happening, how do those queries look like, in order to adjust and choose that perfect token length for our model. And that also gave us very good latency benefits. Number 3 issue is uninformative names. So as we said, we initially relied on product names to do the search. And some products are better for that than others. Like, for example, Cheetos Spicy Flaming Hot Crunchy 8-ounce, 226.8 grams US import is a great product name. It gives us information, both the fact that it's Cheetos, we have the brand, we have the flavor, they're spicy, flaming hot, we have their texture, they're crunchy, we have the size of the product, and also even the fact that it's imported from the US. But not all products are great like that. Other names are like King of the Ring, which could either be a burger or a fighter or anything really. So how do you deal with these items? And that's when we start thinking about including additional features into our model. There are discussions, of course, on what type of features work best, but we're not really going to discuss our features today. But you can get some hints, like we have descriptions on the app that restaurants might include. We have pricing for these items. So all of this we've seen to have a very big impact on how our model performs, especially for these weirdly named items. Then the next question is, how do we include all of this metadata into our model? There's two key different ways to do that in the literature, and that's using early fusion or late fusion. Both have their benefits and disadvantages. Early fusion basically involves combining the features before we put them into the transformer, while late fusion involves doing it afterwards, doing it later. Basically, you would create your embedding using the transformer backbone and also embed separate features using a separate machine learning model, and then combine those embeddings at the end using a linear layer or something more complex. And as I said, there's benefits and disadvantages to both. We've gone with an early fusion approach just because of the benefit of the attention layer that we saw, gave us great advantages. Our transformer model can attend to different parts of our input based on different features. So for example, the pricing of the item could influence how it looks at the title and how it tries to interpret that. And in the literature, there's different ways you can do early fusion, whether that's early summation, where you simply just sum the tokens or average the tokens together, token concatenation, which just simply means appending all of the pieces of all of the tokens or of the pieces of text together. There's even more complex ways like cross attention between transformers, but we stick to the simple token concatenation for ours. So then comes some nice, interesting findings from that, because the absolute simplest way you could combine those is just convert all of your features to text. Oh, I didn't say that, of course, a disadvantage to early fusion is that all of your features that are numerical cannot be handled by a transformer. So, of course, you have to bucket them. So that's a disadvantage compared to late fusion, but it's something that we can stomach. Feature concatenation basically looks something like that for us, basically appending all of the pieces of text together to create a simple text string to input into our transformer. But we wanted to take that a step further, and we saw that in the literature, a lot of people are basically using separator tokens to separate different parts of our text input, all of the different features, and it really helps the model with positional encoding of all of the different terms and consistently locating where each feature is in the input, and that gave us great accuracy advantages. On top of that, Jess wanted to take that a step further, and we tried using custom separator tokens instead of just generic separator tokens. So these are specific to each one of the features, and it really helps locating that feature in the input even better, and great accuracy advantages from that as well, even better. And with that, I can take a breath. Jess.
Can I have a... Yes. No. Oh. Yeah, thank you, Mike. Now we have this model that is able to embed any entity that we want at the moment. But we have different applications, right? So this goes from grocery substitution to search to recommendations, because now we have embeddings for whatever we want. We can use them for them. So we have to balance something. So we have to balance latency and the cost of infrastructure, of training, of maintaining these models, but also we need to balance the granularity of the embeddings according to the use case. Some use case may want to use more information than others that don't need a high granularity embedding. So how do we handle this? Well, actually, it's just that we need to keep a balance. So that we keep training simple, but also we allow everyone in the company to use these embeddings for anything that they want. So how do we try to solve this? So we read this paper called Matryoshka representation learning, in which basically we are able to make the model learn in a way that is nested. So the way that it works is, for example, in gray, we have the full length vector. In this case, let's say 384 dimensions, and we calculate the loss on that. But we also calculate the loss on half the dimensions, and then we half again, divide the length by 8, by 16, and so on and so forth. And we sum all of the losses, and we basically make the model learn in a nested way, in a way that as we increase the dimensions, we increase the granularity of the information. And why is this useful? Because basically we can do adaptive retrieval, in which we can just slice the vector, the shorter that we can, which would be 12 dimensions, and this would be used for shortlisting in search. But then we can use the higher granularity embedding for ranking, and this will basically show the things we're going to show at the top in a better way using this extra information that we hold in the last dimensions of the embedding. Another thing that we can do is adaptive classification, which is basically depending on the confidence that we have to make a classification, we can choose the embedding size that we want. And this is very simple because we just need to slice the embedding. We don't need to retrain something depending on the task that we want to do. So just like a bit more like an illustration, we go back to the Cheetos. We like them so much. So we have the highest dimension, which would be the entire text string would be Cheetos, spicy, flaming hot, crunchy, etc., etc. But then we go to another superclass, which would be just like Cheetos, spicy, flaming hot, crunchy. The next one would be just Cheetos. And then in the lowest dimension embedding, we will have snacks. So basically, yeah, this is what I said about the losses. They are applied at different granularities. So we encourage all the Matryoshka nested vectors to be informative without having to do this, without having to use this extra resource if it's not needed. So I think that's it in terms of takeaways, just like to go through what we went through. The first takeaway is that the pains from keyword matching search can be solved with semantic search, but of course, this brings other issues. We also talked about additional learning tasks that can help with long tail items, or the pre-training that we mentioned on grocery substitution. Then we have quantization and tuning token length, which are crucial for our problem with low latency. And we also talk about early fusion with custom tokens, which is great for the model to learn the context and know what the input that we are inputting is about. And then the fifth one, so nested representation techniques can help by allowing us to slice the embeddings according to the use case needs. And well, we have all of these techniques, but we do need to keep training simple and adapt to the use cases. I think that's it. And this is our spy search.
Thank you very much. That was a lot crammed into a very short space of time. Well done. Does anyone have a question for the Just Eat team?
Really? Okay. Sorry, I was trying to follow, but to the best of my abilities. So you ended up with building a bespoke model to create embeddings,
Yep.
Right? Would you mind sharing how long did it take for you to come up to a point where it was producing usable results that you can roll out into production?
In terms of the Matryoshka part with the multiple losses.
Or just in general from ideation?
Just in general from realizing, okay, the semantic search is what we're going to go with, started experimenting, and then having something that is really usable in production.
It all started from a hackathon before I joined the team. And from that point until production, just a few short months. And we focused on getting the bare bones out. So the two-tower model first, and running an experiment with it. And all of the different issues we encountered and improvements came right after. So just a few short months and first iteration was out. In terms of the Matryoshka embeddings, if that is the question, Jess did that so fast. It was like in a matter of a week we had Matryoshka embeddings. So very big claps to Jess.
Legends.
Anything else? Any other questions?
Yeah. I'm supposed to throw this.
Hope I'm audible. Yeah, so first of all, thanks for the wonderful talk. Great work. So I'm assuming that these semantic search-based model is like already available on Just Eat. So I want to know, when you find these matches, positive matches, how do you decide that is a positive match? Because from my understanding, this gives a similarity score. So how do you decide whether there's like some kind of threshold based on, you're deciding whether that is a positive or not, or you just ranking the results based on the similarity sorted from higher to low?
In terms of retrieving all of the results,
Yes.
it's basically we retrieve the results past a certain similarity threshold. And in order to know what the appropriate similarity should be, whenever we train our model, it's always trained on pairs of query that a user wrote in our searching in the app, and then the item that they clicked. And it's very easy then to evaluate and see, would they have clicked on it where we placed it on the ranking in order to evaluate it. So it would be a recall type metric for our evaluation, for example.
Right. Cool. Thank you.
Anybody else? The question? Yes, sure.
Yeah, the content problem that you mentioned, where sometimes you had something like the Big Blue Burger, which isn't really informative. Outside of the kind of semantic search to solve that, are you thinking of, so it's a problem that my company struggles with as well. Are you thinking of like enforcing content rules, or are you thinking of solving that any way, or do you find any other way, or do you find semantic search sufficient for it?
You answer. I was turning on.
So for a very long time, rule-based was the way to go in our company. So when we say just text-based matching, we're not just doing a traditional text match. There's very specific and complex rules that would go around that. And I think a pattern that we saw, at least in our company, was that these text-based rules were just stacking and stacking and stacking on top of each other, and would start to make search more and more complex. So as much as we can, including features that could give this description and create an informative embedding space for everything, is to us feels a lot more beneficial than having all of these little rules here and there, because they do become unmaintainable and require very big teams after a certain point.
Sure. Can I ask one myself, which is, do you still have text-based matching, or is this replacing all of your text-based matching?
For now, there is a little bit, but the plan is to slowly roll out and automatize everything with semantic.
Awesome.
Thank you.
One last question, perhaps?
Yeah, the question I have is about the noise. So in our experience we were using generic models, so they produce vector similarity brings products that's, yes, there is a vector space connection, but they're just noise. They're not relevant to actually user was actually seeing. Did you have that problem? Did you have to solve that?
Sometimes we had it, and I think that's a point that I should have mentioned in my answer to my previous question. We do still keep a hybrid aspect to it as well. Yeah. So text-based matching is still also there. So the combination, the hybrid search combining text-based matching a little bit together with our semantic part kind of pushes those items down. But we hope through training slowly to minimize those. Sometimes they do pop up, but the hybrid combination usually suppresses them.
Interesting. Thank you.
No worries.
Okay, so I think we'll leave it there. Thank you very much, Jessica. And sorry, I didn't catch your name.
Mike.
Jessica and Mike, please.